All right, so I'm gonna go over the Chat GPT thing, but let me just say something really quick. Okay, so 150 degrees generated here. If it transfers 150 degrees and expels 150 degrees, that is a good thing. 150 degrees generates here. If it transfers 200 degrees and expels 200 degrees, that is still a good thing. But however, if it's 150 degrees and then 142 degrees, that is a bad thing. So, you know, if it can reach equilibrium, that is a good thing. If it's 150 degrees and 142 degrees, that is a bad thing. However, if it's 150 degrees and 200 degrees, that is still a good thing. Anyways, in order to make it 150 degrees and 200 degrees, it just means like how efficient are the cooling pipes in transferring the heat from this thing and this thing. How efficient are the radiators in expelling the heat? Like, are they advanced radiators and advanced cooling pipes? If they are, great, then you can perhaps achieve the goals of 150 degrees and 200 degrees. That would be with advanced radiators and advanced cooling pipes. Cooling pipes. Anyways, I remember a couple of days ago I saw a YouTube video. I forgot what I searched up. It was something about radiators because ChatGPT was mentioning things about advanced radiators and like 300K, and I was thinking in terms of measurements and things like such as what is it called, like radiator, it's some type of advanced radiator. It's like a radiator drop thing. Radiator. Hold on. I think there's a picture of it, so it might be easy to find. ChatGPT did tell me about this type of radiator that is more advanced radiator. I just do not remember what the name of the radiator is called. Oh my gosh. Oh, it's called a liquid. Yeah, the thing that ChatGPT suggested, the more advanced radiator, is called a liquid droplet radiator. Apparently, it expels heat at a much faster rate using like whatever it uses. But it said like, it expels heat at like 700K versus 300K, in which that's just like a measurement. The radiator expels heat at 700 kelvins versus traditional radiators expels heat at like 200 kelvins. So 200 kelvins less efficient, 700 kelvins more efficient, more advanced radiators. But ChatGPT said that the more advanced radiators to expel heat at like 700K, the radiators have to be operating at very high temperatures and whatever. And it said that these more advanced radiators are very easy to malfunction after operation if it is not maintained properly. Whereas traditional radiators that goes to like 200 kelvins, they are less likely to break and less likely to malfunction, although they are much heavier and apparently they are much larger. So like for instance, ChatGPT provided an example saying that like the like a traditional radiator that is 300K, or I guess like 300 kelvins, it is about, in terms of the radiator size, it said something like two kilometers squared to 3 kilometers squared in size. And in order for me to like get a visual of how large this thing is in terms of distance, it said that like a place in New York, like the New York Garden, this could be like the New York Square Garden or some type of New York very prestigious garden. The total size of this place right here is about, like, let's just say on the lower end, about 2 kilometers squared. So I've never been to that place before, but if this place is 2 kilometers squared, that is a very large distance in terms of length and width. And if this radiator needs to be that big, that just is about 300 kelvins, that's insanely large. Anyways, the more advanced radiators, like the more advanced radiators would be something like advanced radiators or liquid drop radiator, is much smaller in size. So it is about the more advanced radiators are very effective and they're very efficient in expelling heat and transferring heat, that they can reach up to like 700K slash 700 kelvins, which apparently that's like this was 300 kelvins, traditional, advanced 700 kelvins, and apparently from that jump it's just like 500 times in difference. I mean, like a very significant difference in heat expulsion and heat transfer. So 150 degrees Fahrenheit and 200 degrees Fahrenheit. Very effective with using these things. And these things are about, in terms of size, rather than it being 2 kilometers squared, it says it is about 0.1 kilometers squared. Okay, so these things would be in size of like 0.1 kilometers squared, which is much more achievable to actually build, because building one object that is this distance and only expels like 300 kelvins, that's not very efficient, because that would be like 150 degrees and 140 degrees, and so that would not be reaching equilibrium on a consistent basis, not be. And so, these more advanced radiators are going to be something that people might have to look into more and perhaps build. But however, remember, these more advanced radiators are more prone to breaking and more likely to malfunction because they have to operate at such high capacity. And so, basically, well, this video, this person was explaining about like radiators with heat pumps, kind of similar to how a refrigerator works, and things that use heat pumps and how effective those things are. And anyways, going back to like what these words mean, I was asking ChatGPT about it, and apparently I mean heat is transferred to radiators in a given moment to reach equilibrium, or 150 degrees and 200 degrees, to have more consistent plus constant heat expulsion, maintaining a perfect balance. That is very important. I would say that it is better to have more radiators. Okay, so having more radiators and more heat expulsion is better, which will correlate to less heat generated. That is better. And then it is worse to have less radiators and less heat expulsion and more heat generated. Like basically these two things are the opposite. Which would go along the lines with advanced radiators, but those have problems. And so anyways, I was explaining it to ChatGPT, and well, just hold on a second. Okay. In this example, I used kelvins and converted it into temperature measurements because I was looking at another video, like this video, and thinking about kelvins in terms of like heat measurements, temperature measurements. 300 kelvins, 80.33 degrees Fahrenheit, 600 this one, 700 this one, etc. And then ChatGPT was just like, oh no, they're not talking about 300K and 700K as not as it is not heat expelled. These numbers are actually radiator operating temperatures. So the radiators need to be operating at these temperatures all the time, I guess. And the more advanced radiators, they can achieve these numbers, but they're more likely to break, and they're expensive and things like that. Traditional, but these are very big and bulky, and 2 kilometers squared New York Garden. These are smaller but much more difficult to maintain. Anyways, okay, and then I said about the aspect of traditional radiators using this and more advanced radiators using this, and also smaller size, larger size. And then because it was just getting very confusing, because there's a lot of other hypothetical things to think about if you want to think about those things. But I just ended up saying, like, after inputting all of this information, I ended up saying, how would you slash ChatGPT design this radiator farm to effectively expel heat? And then ChatGPT was saying, like, okay, well, if you want to effectively expel the heat to maintain equilibrium 150 and 150, or 150 and 200, then you want to think about establishing level 1 radiators, which would just be traditional radiators, and these traditional radiators are just going to expel the heat from data centers for basic data center usages. That would be for level 1 radiators, level 1 radiator farm. And then if the data center is using more electricity and the data center is using more sophisticated AI software, AI is doing like this, like generating videos, generating pictures. AI is thinking for itself. AI is analyzing these very complex things, and it is using more heat. It is generating more heat. You're going to have to be using level 2 radiator farm. So, basically, to explain it, you would have data center, and then for the radiator farms, you would have level 1 radiator farms, which would just be the traditional radiators. The traditional radiators, which are larger in size. They are larger in size, like this one, and they can reach like 300 kelvins. They are more robust, less likely to malfunction. That is important. But however, these traditional radiator farms, they would be used for like the data center using very minimal data, as an example, this would be associated with minimal data, minimal heat buildup, such as text stuff plus phone calls. I'm pretty sure those are not very data intensive, plus etc. Apparently this can figure out itself on its own. And then after building level 1 radiator farms, then you have another separate radiator farm called level 2 radiator farms. Level 2 radiator farms. And these would be for the more advanced radiators that can be, get to like 600 kelvins slash 700 kelvins. And remember, even though these more advanced radiators are more efficient in terms of this number right here, and they are also smaller in size, so rather than being 2 kilometers squared, they are about 0.1 kilometers squared. You can build them very quickly because they're so small, but they are less robust and they are more likely to malfunction. So that is the negative aspect about those things. And these things would be mainly be used as like a backup measure whenever there is very intensive data usage spikes plus heat plus very intensive heat usage spikes plus like plus etc, such as AI is doing very sophisticated things, like AI is generating videos on its own, or AI is analyzing very complex things, which involves AI thinking, and AI is doing the aspect of advanced calculations and searching through like different formulas to find like the correct formula. Very intensive stuff. That is when these advanced radiators will kick in. But the level 1 aspect is the traditional radiators, and then the level 2 aspect is the more advanced radiators. In order to create balance, this mainly does most of the work, because most of the time it's operating with it is operating with expected data usages and expected heat temperatures. But however, every now and then there will be these massive spikes, and in order for these massive spikes to keep everything in equilibrium, you need to have the more advanced radiators. So like it could just be like, if they wanted to, for like one data center, it could be like 10 traditional radiators, although I'm not sure about the price of this, but 10 traditional radiators, and let's just say 3 advanced radiators slash, or it could be 10 traditional radiators and 1 advanced radiator, just to see how things go. Okay, anyways, hopefully you have understood what I was talking about. Hopefully you have understood what I was talking about. Anyways, now I guess I'm going to read this ChatGPT explanation. Okay, and this will go through the entire process. If you want to watch the rest of this video, you can. If you do not want to watch it, you do not have to. I'm just saying that this is going to be like a very long. Okay, anyways, so my response that I said is is this realistically possible? I always thought that data centers in space, those data centers in space would be built by doing: 1. You construct the data center on a planet like the moon. The moon has the advantage of regularly reaching extremely cold temperatures because of no atmosphere. 2. There is a space-based solar panel orbiting in space orbiting the moon. This thing is, this space-based solar panel uses sunlight, converts the sunlight into electricity, stores the electricity somewhere temporarily. There's no atmospheric interference in space, so that means more efficient at generating sunlight and converting it into electricity. When space-based solar panel gets closer to the data center target, it orbits around in space. Like it orbits around in space. And then once it gets closer to like this target right here, it will then, because it got closer to the target, it will then beam down the electricity to the target via a laser beam, or microwave waves. Although, the main aspect you have to worry about is if it misses the target, which could happen. But anyways, it beams down the electricity. Target receives a lot of electricity because of Moon's very weak atmosphere. No atmospheric interference. 4. Moon data center is supplied with tremendous amounts of electricity. 5. Just have to make sure that the beaming down of electricity, this does not become a laser death ray / electricity death ray, because if it misses, very bad. ChatGPT says, yes, in principle, something very similar is physically possible. In fact, your idea combines two concepts that engineers and space agencies have seriously studied: lunar data centers on the moon, space-based solar satellites, power. The main challenges are economic and engineering, not violations of physics. What works well about your idea? The moon is naturally cold. The moon's surface can become extremely cold during the lunar night, especially inside permanently shallowed craters near the poles, near the lunar poles. However, remember, never mind. Data centers spend enormous amounts of electricity on cooling. A cold lunar environment could potentially reduce cooling costs. Even though the air temperature of the moon is cold, it does not necessarily mean that the data center is going to be cold, because the moon has a very weak atmosphere, and then coolness or hot can only transfer to an object via the process of conduction. So, that's a problem. If it was convection, it would, work how it is on Earth, because there's wind and stuff. Oh my gosh. However, there is a catch. Computer chips do not just need a cold environment. Computer chips need a way to remove the heat. That's what I explained in here and what I explained earlier. In a vacuum, there is no air for fans to blow across heat sinks. So a lunar data center would still need radiators, it would need heat pipes or cooling pipes, it would need thermal management systems. Ironically, cooling computers in space can be harder. It can be harder in space because no atmosphere, and cooling them on Earth is easier because there is atmosphere. No atmosphere conduction with an atmosphere convection. Space-based solar power is a real concept. The idea is huge solar arrays in space, like space-based solar powered satellites in space collecting sunlight. Sunlight is converted into electricity. Electricity is converted into microwave waves. Apparently that's safer. Or lasers. That's more dangerous. Beam down with lasers, more dangerous. Beam down with microwaves, safer. And then energy is transmitted wirelessly to a receiver. Many organizations have researched this concept, including NASA, the European Space Agency, and Japan Aerospace Exploration Agency. Advantages: no clouds in space or on the moon, no weather in space or on the moon, near continuous sunlight depending on orbit. Solar panels in space can generate more consistent power and more consistent electricity because of no atmosphere than solar panels on Earth. Weak because of atmosphere, strong because of no atmosphere. The moon has no significant atmosphere. This helps transmission. A laser to beam down the electricity or a microwave to beam down the electricity aimed at a lunar receiver, the target site would suffer or benefit from very little atmospheric loss, no atmospheric loss because the moon essentially has no atmosphere. This means more energy reaches the target. The death rate problem, this is a real problem. This is exactly what engineers worry about. And there's ways to get around with this because remember, the data center still needs to be powered via electricity. So, ways to work around it. You could have solar panel satellites. They do what they do. They're in orbit in outer space. They receive sunlight and then they convert the sunlight into electricity and then they beam down the electricity to moon's surface, to the target. However, you gotta worry about death lasers and death beams if it misses the target. But that's very effective. Very effective on a consistent basis. And then you also can have solar panels on moon's surface, but you still have the meteorite impacts, plus that can cause damage. The meteorite impacts plus extreme regular temperature differences, if that will do anything. Plus apparently I guess there's like solar radiation and whatever. I don't know if that does anything or not, but apparently since you have 14 sun days on moon plus 14 nights on moon. Okay, so for the Sundays, that will be good for the solar panels, but for the nights, it's just, are you going to have enough electricity? So apparently, according to the nights, that is less effective. On a consistent basis. Okay, and then for the nights, you would also need something like a battery storage area for electricity, which is a whole nother thing to think about and properly take care of. So it's just the most consistent aspect, the most consistent source of electricity / energy for the data center is once again going to be nuclear energy. Although some people will be scared of nuclear energy because the nuclear energy or the nuclear reactor, let's call it that, it could malfunction and leak radiation everywhere, and that will be a disaster. it could explode. That will lead to a nuclear explosion. That's a disaster. And plus, you have the meteorites striking it. You do not want that to happen. I guess you could construct it underground because you prevent the meteorites impacts because you do not want this thing to be penetrated with holes. You do not want this thing to break and explode. But this thing is quite literally the most consistent source of electricity and energy for the data center. And also the nuclear reactor. And also, can a or can nuclear energy power a data center? Oh my gosh, data centers are gonna make this much worse in the future. But anyways, can a nuclear can nuclear energy or a nuclear reactor power a data center? Oh my gosh, it says yes, some data centers are beginning to use nuclear energy because it's the opposite of electricity to meet the demands of AI and data centers and whatnot. It helps out people and lowers electricity costs. But remember, if this thing explodes, if this thing starts leaking if this thing explodes, huge disaster. If it starts leaking radiation, huge disaster. But however, nuclear energy, nuclear reactors to power data centers on the moon is once again the most viable option plus consistent option to meet the needs of moon data center. So viable option, the most consistent option to meet the needs. Potentially some people could say it's like the most option that results in the least problems. I mean, there is the problem of radiation, the problem of a nuclear explosion, but without just thinking about those two things, if you think about the other things such as laser beams of death, electricity laser beams of death, and they become laser beams of death if they do not reach the target, then you see that nuclear reactors and nuclear energy to power the data center on the moon is realistically the most realistic option, the most viable option, the most consistent option to meet the needs of the moon data center, and the option with the least problems attached to it. I mean, with electricity and space-based solar panels or space-based space-based solar with these things, it is very difficult. Like, it will be very difficult, especially in the long run, because remember, this thing, once it once it collects enough electricity, it has to beam down the electricity to the desired target. And if it misses the target, that is going to be very, very bad. I mean, it's going to be, if it misses the target, it is going to be not as comparable to a nuclear explosion. It is going to be, like, if this thing misses the target, it is going to be less devastating than a nuclear explosion. But, I mean, I don't know. The nuclear reactor to power the data center on the moon is more, it can be implemented. I mean, this can be implemented as well because there's different options too. I mean, if you want to go down this route, you can. It's just, there's a lot of hypothetical things that could go wrong. The nuclear reactor, there's a lot of hypothetical things that could go wrong. In terms of like devastation, this could be less devastating. It just depends on, it just like the nuclear reactor exploding. I do not know how devastating that would be. But this thing, it beaming down the electricity, I do not know how devastating it would be. I mean, this thing right here, these things could technically be done. Although, it's just what is more viable and what can produce the amount of electricity for the data center on a consistent basis. Oh my gosh. All right, death ray problem. The amount of electricity that the data center needs. And then it fails, the beaming down fails, software malfunctions, guidance systems are hacked. Then the beam could hit somewhere that it should not do and cause, I mean, I don't know, I do not even know what it would cause. So this would be a safer alternative, microwave beams. Lasers can be more dangerous. Okay, I'm trying to just get through this without having to go through this entire thing. An even more likely future, so right here, instead of having solar station orbiting moon data center, you might see solar station in orbit around Earth, solar station in orbit around the moon, lunar data center near the moon's south pole, AI systems operating locally on the moon. Basically, just whatever. Okay, and so this is the part where you get into the aspect of conduction for no atmosphere planets. So on Earth it's convection because there is an atmosphere, but on the moon it is conduction because there is no atmosphere. The cooling problem is different in space. Many people think that space is cold, so cooling should be easy. But however, the cooling is often harder in space because there's no wind, there's no atmosphere. You can only cool stuff through the process of conduction. This has to do with a certain aspect. In no atmosphere environments, in a vacuum, there is no air, there is no wind, there is no convection. The only way to continuously get rid of heat is by thermal radiation, conduction, transferring heat, and heat being expelled via radiators on the surface into outer space. Server data centers generate heat. Heat is transferred to pipes through conduction, and heat travels through pipes, and then heat is transferred to the radiators, and then the radiators expel the heat into space. Um, besides that point, could lunar night, could negative 150 degrees, could negative 150 degrees Fahrenheit help in cooling down the hot components? Yes, during lunar night, negative 150 degrees Fahrenheit, surface temperatures can become extremely cold. A data center could potentially store heat underground, radiate heat towards the cold sky, but even then, this would have so in this example it could happen, but the heat would have to travel in an upwards direction. You know, the data center the data center generates heat, and then the heat would have to travel in an upwards direction, and you know through the process of convection. But since there's no convection, there's only conduction, it does not really help. So anyways, I'm basically trying to explain what's actually happening. Conduction, conduction, but even then radiators are still needed because of conduction, which is right here. Radiators are needed if there is no atmosphere. Radiators are needed if heat is only expelled via conduction. Right here. Radiators are needed for this thing right here, for heat to be properly expelled. Radiators are needed. This is the problem with solar surface surface on the moon's surface, solar farms on the moon's surface. The problem is about the 14 Earth days of darkness on the moon. The satellite is a better aspect because it's always receiving sunlight. Collecting solar energy, collecting sunlight, converting into electricity in space is relatively easy and straightforward. That is the easiest part. The difficult part is beaming down the electricity via laser beams, electricity beams, or microwave beams to the desired target very accurately. That is very difficult, and doing it over long distances is very difficult because if you miss it, oh my gosh, that could cause lots of devastation. So, the moon has no atmosphere, the moon has no wind, and I said, to more explain it, I said, if the data center generates heat, will the heat be able to rise in an upward direction? So, if the data center generates heat, will the heat be able to rise? Will the heat be able to rise in an upward direction? However, that is not true at all on the moon. That is not true. That does not happen in no atmosphere planets because heat can only be transferred through the process of conduction, whereas on Earth heat travels in an upward direction naturally because of the process of convection, which just means that heat rises because it has to do with heat molecules are less dense, and then cold air swoops down underneath the heat molecules, and the cold air cools things, but that only happens through the process of convection right here. And it has to do with hot object. The object becomes hot, the data center becomes hot, and so the data center becomes hot, and so the air around the data center becomes hot. Okay, it warms up, the air around the data center warms up, and then the warm air becomes less dense, and this is the key aspect, it becomes less dense. And so because the warm air becomes less dense, the warm air rises because it is less dense. And then the warm air is less dense, and then the cooler air, which is more dense, the cooler air moves underneath to cool the data center because there's wind and there's the process of convection. But for the moon, no atmosphere, you have to rely on the process of conduction. And I explained it in the beginning of this video. It can be kind of difficult, but it has to do something like with conduction. This is on the moon, no atmosphere. Heat can only be transferred, or heat can only move through other solid objects. So as an example, the server gets hot, the data center gets hot, and then the hot is transferred to the metal rack, a solid object, and then the metal rack gets hot, and then it is transferred, and then the hot is transferred to a cooling pipe, another solid object, and then the cooling pipe gets hot, and then it transfers heat to a radiator, another solid object, and then the radiator is exposed to outer space, and it fully expels the heat. But that's the process of conduction. So conduction to remove heat, to expel heat, is a process, and convection to expel heat is another process. They're two completely different processes. Harder, it can be done, but it's harder. It is more easier. The heat travels through physical contact. And then you have thermal radiation, or expelling the heat into outer space. Everything above absolute zero emits infrared heat. A hot object on the moon, like the radiator, since it's hot, will radiate heat directly into space, directly into a vacuum. And so that's how to successfully expel 100% of the heat. The radiator emits heat into the blackness of space. And also, hopefully you have understood my example about how to expel heat through the process of conduction. Okay? And also, you need to think about this. So think about this. Radiator expels heat into space. Heat is essentially like gone to zero. However, this is also massive amounts of heat, continuous amounts of heat, and the heat is always being expelled into outer space. Okay, and now outer space just does what it does with the heat. And so I guess you could say, since the heat is always being expelled into outer space, I guess you could say, is there ever going to be the aspect of too much heat in space? Space gets so hot, or outer space gets so hot. If you know what I'm talking about, outer space is getting so hot because of so much heat being expelled into outer space. Does it ever get so hot? Kind of similar to things such as climate change on Earth, plus global warming levels rising on Earth, plus ocean temperature levels rising on Earth, and it's just bringing absolute destruction to Earth. Does it ever happen does space ever get so hot? And I remember asking Apple AI about this question, and basically Basically, it said with this aspect, all of this heat is being expelled into outer space. Will outer space ever get so hot? And basically, what the Apple AI said is this. It says no, outer space will not become too hot even if there is massive plus tremendous tremendous amounts of heat being expelled into outer space. So the basic answer is that no, you are is no. It will not become too. It will not become too hot. You are completely fine, even if you were to expel 1 million degree Fahrenheit of heat into space. You are completely fine, because the reason why the AI said something is outer space is constantly expanding all the time. Okay, so it is always getting bigger, always getting bigger plus growing larger to infinity, forever essentially, which just means it just means that, like, if you were to expel 1 million degree Fahrenheit into space, then yes, temporarily space will become hot. Okay. However, over time, because outer space is so big and so large, and plus there's also the aspect that it is always expanding over time, the heat in outer space, the heat will eventually disperse. Like, you know, the heat to think about it, when 1 million degrees is expelled into outer space, it is this one giant ball of heat, and it makes things very hot. However, over time, the ball will slowly start dispersing. The ball will slowly start becoming thinner and thinner and thinner and thinner, because, you know, space is so large, and also it is expanding all the time. It is getting bigger and bigger and growing infinitely larger over all the time. And so the ball will just keep on being stretched out and stretched out and stretched out until it becomes like a like it becomes so stretched out, as thin as a rubber band. So, you know, you went from a ball, which is very large, to a rubber band, which is very stretched out. And so you do not have to worry about the problem of space becoming too hot. Space becoming too hot is not a problem. Earth becoming too hot, so, you know, space becoming too hot is not a problem, according to Apple AI. But Earth becoming too hot, which leads to, you know, like climate change, global warming levels rising, ice caps melting, weakening of Earth's magnetic field. Um, but these are problems. Earth becoming too hot, that is a problem. Plus a major problem in the long run. But for space, I mean, I guess you could say you kind of do have to worry about it, but essentially you do not even have to worry about it. And not only that, but if data centers on planets are successful on the moon, and you also have moon's gravity measurement, and moon does not have moon is not like Venus or Saturn or whatever, then you can probably install data centers on other planets as well. And it's just like, oh, do not worry about this stuff. But anyways, I just went into something about you do not space becoming too hot because of too much heat expulsion is not a problem. Okay. In this example, you have a hot metal cube in a vacuum chamber with no air. The metal cube is going to be hot, and the hot metal cube, the heat does not rise in an upward direction because there's no convection, there's no air, there's no wind, there's no convection, and so the metal cube will continue to stay hot, and the heat will be contained inside the metal cube because no atmosphere and conduction. The heat will not float in an upward direction. However, the cube heats nearby structures through conduction, and these structures have to be connected to the hot cube. Similar to this example, if you know what this example is in reference to, and using the process of conduction. Nope. Because there is no atmosphere, no hot air, less dense air forms, and no heat rises, and no cool air goes underneath to cool the data center because of no atmosphere and conduction. The heat of the hot metal cube, the heat of the data center, must physically travel through cooling systems. The heat must physically be transferred to cooling pipes and transferred to radiators that are connected before being emitted into or before being expelled into space. Hopefully you know what this example is in reference to. Hopefully you have gotten a good picture. Okay, I think I'm just going to skip around. If the data center consumes 100 megawatts of power, nearly all 100 megawatts, it will eventually become heat. So 100 megawatts becomes heat. And then engineers must design radiator systems capable of continuously, very efficiently to reaching equilibrium, radiators that will emit roughly about 100 megawatts of heat into space within a very short period of time to maintain equilibrium. Such as this example right here. 150, 150 maintains equilibrium. 150, 140, failure. 150, 200, success. I tried explaining it into ChatGPT, like explaining how convection works and how heat rises. I mean, I explained it in a good way. Like on Earth, for data centers on Earth, when components get hot, um, two, air near hot object warms up. The air warms up. Three, the warm air becomes less dense. The key word is less dense. The warm air becomes less dense and it rises up. And then because the warm air rises up because it is less dense, less dense air equals allows the heat from component to rise. Because of heat from component rising, cooler air moves underneath, allows for cooling. Convection, that is an aspect of convection right here. Convection. Process of convection. Convection happens when planet has a strong atmosphere. For planets with an atmosphere, like Earth, convection. For planets with no atmosphere, like the Moon, conduction. Convection does not happen on the Moon, no atmosphere. Convection happens not on planets with no atmosphere because of no wind plus etc. And then, this is what happens for no atmosphere planet. Moon data center component. The component becomes hot. 2. Heat originally stays trapped in the hot object because of no convection. And 3. Heat object can only transfer heat to another solid object because of conduction. Convection is also a much easier way for heat to be expelled. Conduction is much more difficult, but it can be done. And the example is like a submarine submerged underwater. The waves touching the submarine are the thing that cools it down. Whatever. I wrote that heat is trapped inside the component with no atmosphere environments. Not necessarily. Heat is only trapped inside the component if the component is poorly connected to a cooling path. So, if there's nothing connected to it, it is trapped in there all the time. The heat is trapped in there all the time. If it is poorly connected to it, then it transfers heat very poorly. But if it is very goodly connected to it, then heat transfer is much more optimal. Okay, anyways, let me just skip around. best place for the data center is underground. All right. Okay, I guess I'm going to skip to, the radiator needs to have a large surface area to effectively expel heat very effectively. But if the radiator is a more advanced radiator, then it can have a smaller surface area. Underground data center plus the radiator is on the surface of the moon is actually ideal. Underground, the servers are shielded from meteorites and radiation. The surface, the radiators or the radiator fields are exposed to outer space, or a vacuum allows for successful expelling of the heat. Hopefully you have understood what this picture means. There's traditional radiators, and then there's more advanced radiators, and then there is a liquid droplet radiator. So something like a liquid droplet radiator, which I guess you can look up on your own, but 700K or 700 kelvins, very, 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 very efficient. I guess I will try to post this ChatGPT conversation to Reddit so other people can read it, because they can read it for themselves if they want to. This thing, your radiator farm idea or whatever, is just another thing about what this picture looks like. And you can design the actual thing however you want it to, but it basically has to do with concepts that was explained earlier in the video, and the concepts explained in this picture right here. Okay, anyways, you can read that if you want to. And in this example, I am just explaining how to think about these things in terms of measurements, but it's a lot. You don't really need to think about it that specifically. You just need to make sure that you know how much the data center, how much electricity and how much heat it might produce in total, and you need to make sure that the radiator farms are able to handle 500 degree Fahrenheit of heat within a given moment, and that the cooling pipes are very efficient in transferring heat. The radiators are very efficient in expelling heat, like 150 degrees and 200 degrees. 150 degrees and 150 degrees. Successful or above successful. 150 degrees and 150 degrees successful, or 150 degrees and 200 degrees above successful. That's what you need to mainly do. Anyways, going from 300K radiator to 400K radiator, or 300 Kelvin radiator to 400 Kelvin radiator is astronomically better, like 16 times better or something like that. Anyways, you need to think about everything in terms of measurements. I mean, you typically do, but I was thinking about things in terms of measurement in a much more complex way. But basically, in order to solve the problem, you need to have in order to solve the problem, you basically just need to have a radiator farm that is, you have the data center generates the heat, and then the cooling pipes transfers the heat, and then level 1 radiator farms made out of traditional radiators does your basic, most realistic stuff, and then you have your level 2 radiator farms, and these are for backups and these are for whenever there's a massive spike. These kick in. And then, here are some numbers. Here are some numbers. These are the problems with advanced radiators. Problems at high temperatures. The materials can weaken, that's a problem. The coolant must survive extreme heat. The pumps must become harder to build. The electronics must be thermally isolated. And it's just like, it can just malfunction and become destroyed very easily if it is used very quite on a regular basis. But that is why you need level 1 radiator farms, traditional radiators, and level 2 radiator farms, more advanced radiators. They balance efficiency versus survivability. Survivability would look something like level 1 radiator farms, traditional radiators, and level 2 radiator farms, more advanced radiators, would correlate to survivability and efficiency. Traditional radiators, more advanced radiators, and liquid droplet radiators, however that is built. Hot liquid is sprayed into droplets. Each droplet becomes a tiny radiator. Total surface area becomes enormous. Like the tiny droplets are mini radiators. And this is how it should look like. Effective heat expulsion is that radiators potentially expel heat faster, and the data center components generates heat more slowly. So data center heat slowly, radiators expel heat faster, radiators faster, data centers slower. Heat expulsion is very effective. Equilibrium is reached. above equilibrium is reached. And you can read this if you want to. You can read that if you want to. Basically, in this video, so this video is by articles by a physicist. Here's his name right here. And it is called Space Data Centers. Can you shrink the radiators? Basically, he was talking about a more advanced radiator, a radiator with heat pumps. And, that's what he was saying in this video. If you want to watch this video, you can. There's a couple of comments on this video. I replied with this comment, but, I'm pretty sure this comment is kind of wrong. Yeah, it would be wrong. Because what he is talking about, in this video, what he is talking about that the radiator expels heat faster and the data center generates heat slower. Radiator faster, data center slower, can be sustained above equilibrium. Level 1 radiator farm for basic operations. Level 2 radiator farms whenever there are massive data spikes or massive heat spikes. And you're trying to create survivability. Hybrid system. Level 1 radiator farm, level 2 radiator farm. I'm pretty sure somebody else knows what I mean by hybrid radiator farm and level 1 radiator farm and level 2 radiator farm. Oh, okay, anyways, I think I am done with this video. Unless I can think of something else. Nope, I cannot think of anything else.